Hey everyone! In this video, I want to take a look at another related rate example. In this example, we're going to be taking a look at spheres, and we actually end up having to use more than one equation to relate our variables together. So the example says the radius of a sphere is increasing at a constant rate of 2 centimeters per minute. At the instant the surface area becomes 64 pi square centimeters, find the rate in cubic centimeters per minute at which the volume of the sphere is increasing. So again, just related rates in general are rates of change that are directly tied to each other. So as the radius of my sphere increases, the surface area increases and also the volume increases. So I have multiple variables going on. The first step, let's just think about what equation we want to use to relate all of this together. So I know I want to find the rate of change for the volume. So I definitely want to use my volume formula for a sphere. So the volume of a sphere is 4/3 pi r cubed. Now it also mentions the surface area. So I'm actually going to have to end up using this equation as well. So the surface area of a sphere is equal to 4 pi r squared. So we're going to take those two formulas and we're actually going to combine those together to find our answer. Now let's take a look at what else we have. So we have a couple different rates of change. So we have the rate of change for the radius, so the derivative of the radius with respect to time. We know that this is increasing at a rate of 2 centimeters per minute. We are given that the surface area is going to become 64 pi square centimeters. So capital S is equal to 64 pi square centimeters. And then what we actually want to find, it says find the rate at which the volume is increasing. So we actually want to solve for the derivative of the volume with respect to time. So that's all the information we have. So we know the derivative of the radius with respect to time, we know a specific surface area we want to end up at, and we want to solve for the rate of change of the volume. Okay, because I want to solve for the rate of change of the volume, I'm going to go back to my volume formula. Now I'm going to differentiate this with respect to time. So that's going to be dv over dt. And now taking the derivative of the right-hand side, we can just use the power rule. The 3 will come down out front. 3 times 4/3, the 3's simplify, so we just end up with 4 pi r squared. And this will be multiplied by the derivative of the radius with respect to time. Now this is where our second formula is actually going to come in. So this 4 pi r squared, this is our surface area. So that's the other formula we laid out up here. So that means I can just substitute this entire expression with 64 pi, the surface area that we're given. And while we're doing that, why don't we substitute in the other things we know? So I know I want to solve for the rate of change of the volume. This is surface area. We know we want the surface area to be 64 pi. And the rate of change for our radius was 2 centimeters per minute. So we're going to multiply by 2. So that means that our volume is increasing at a rate of 128 pi cubic centimeters per minute. So again, our related rates, these are rates of change that are directly related to each other. So as the radius of the sphere increases, that also affects the volume, and our volume is also increasing. Same thing with the surface area. So the process, we decide on what formula we want to use. Taking a look at the information we have, we knew that we had to use the formula for volume, differentiate that formula, plug in our known information, and solve for that unknown rate.